In this video, we're going to take a look at how to solve exponential equations. In general, this would involve taking the log on both sides, since a logarithm is the inverse of an exponential, or in other words, it takes the variable out of the exponent. If the base of the exponential is e, then we'd be using a natural log, and if the base is 10, remember that means we'd use a common log, which is just written as log, and there's no base specified. In some equations, you're able to make the base the same on both sides, but there aren't any examples of that in these notes, so we're going to write our own. For example, we could have an equation like 3 to the x power equals 9 to the x plus 2 power. And since both sides of this equation can be written in terms of a base of 3, let's do that. I'll leave the left side the same, but we can take 9 and rewrite that as 3 squared, and then keep the x plus 2 power on the outside of the parentheses. So now we have a power raised to a power, and that just means that we have to multiply the exponents. We do have to be careful though, because this x plus 2 is a binomial, so we're going to have to distribute this 2 into both of those terms. So again, the left side is 3 to the x, but now the right side is 3 to the 2x plus 4 power. And now all we have to do is take the log on both sides. And since the base is 3, I'm going to take the log base 3 of both sides. So the log base 3 of 3 cancels on both sides, and on the left I'm just left with this x, and on the right side I have the 2x plus 4. So I'll get both x's on the same side and subtract the 4 over to the other side, and x equals negative 4. I want to do one more example where we have a fraction involved, because sometimes you'll see something like this. 2 to the x power equals 1/4 to the x plus 3 power. So on the left side, this is a pretty simple base of 2, and on the right side, I think I can rewrite this 1/4 as a base of 2. So 2 to the x equals, and then let's think of how I can rewrite this as a base of 2. So I'd want to change this whole number into a fraction, which means I'd want a negative exponent, and 2 squared is 4, so 2 to the negative 2 power is 1/4. And then I'll keep that to the x plus 3 power. So now I can distribute this negative 2 into this power on the right, and then take the log base 2 on both sides, and that's how I can cancel the bases and get the variables out of the exponents. So now I just set the exponents equal to each other, and x equals negative 2x minus 6, so I'm going to add 2x over to the left side, so I'd have 3x equals negative 6, and divide by 3, so x equals negative 2. For the rest of this video, we're just going to look at different examples of solving exponential equations, so if you feel comfortable with any of these, I'd encourage you to stop the video and try solving them on your own, and then just check your work against mine. In these first two examples, the key steps are going to be to isolate the exponential term, and then take the log of both sides. So for example, in number 1, the exponential term I want to isolate is 3 to the x power. So I'll start this by adding 4 to both sides. So then I have 2 times 3 to the x equals 54. And now I can divide both sides by 2. So 3 to the x equals 27. And then 3 to what power equals 27? You might be able to solve that in your head if you know that 3 cubed is 27. But another thing you could do is just take the log base 3 of both sides. Over here, the log base 3 of 3 cancels, and I have x equals. And then the log base 3 of 27 could be typed into some calculators, but if yours can't handle a different base, you could use the change of base formula, which says to put the big number on the top of the fraction and the original base on the bottom of the fraction. And now we're changing this to using the common log, which can be typed into most calculators. But of course, we should get x equals 3, just like we saw over here. In number 2, I'm trying to isolate the 2 to the x over 2 power. So the first thing I'll do is divide both sides by 3. And now I have 2 to the x over 2 power equals 10. Now this one I can't do in my head because 2 to some easy power is not 10. So I'm going to have to take the log base 2 of both sides. On the left side, the log base 2 of 2 goes away, and I have x over 2 left over. And now over here I could type this into my calculator or change it to the log of 10 over the log of 2. And again, that's using the change of base formula. And actually this much, log of 10, I know that because log base 10 of 10 is 1. So x over 2 equals 1 over the log of 2. And now if I just multiply both sides by 2, these will go away, and then I have x equals 2 over the log of 2. As a decimal, that's about 6.6. In number 3, the variable we're trying to solve for is really buried because it's in this exponential term, and it's being added to 2 inside this denominator. So the first thing we'll have to do is get this whole thing out of the denominator, and I'll do that by multiplying both sides by 2 plus e to the x power. So these cancel out, and I'm left with 3,000 equals 3 times 2 plus e to the x power. And it's tempting to distribute this 3 in, but instead of doing that, let's just divide both sides by 3, because that gives me 1,000 equals 2 plus e to the x. And then if I subtract 2, I get 998 equals e to the x. So now I just have to get rid of this base e so that I can get the variable out of the exponent. Since it is base e, I'm going to take the natural log of both sides. So on the right side that cancels, and then I get x equals, and then if you can just type that into your calculator, you get about 6.91. So in that problem, the key thing we had to do is get x out of the denominator. In this next problem, the trick is that this is set equal to 0, and that's my cue that I should factor this. If you actually thought of this as x squared plus x minus 6, you would see that you could factor that into x plus 3 and x minus 2. So the only difference is we don't have x squared, we have e to the 2x. And if you wanted to, you could think of e to the 2x as e to the x squared, and then at least the bases would be the same just like they are over here. So if you rethink this, now you could see you could factor this as well, right? So it would be e to the x plus 3 and e to the x minus 2. Because I'm looking for two numbers that multiply to negative 6, and they have to add to 1. But now that this is factored and set equal to 0, I can just set each of the factors individually equal to 0. So on the left I have e to the x equals negative 3, and on the right I have e to the x equals 2. In both of these equations, I'm just going to be taking the natural log of both sides. So natural log of e to the x equals natural log of negative 3, and these would cancel, but then I'd have x equals the natural log of negative 3. And if you don't remember previously learning this about logs, you can't take the log of a negative number, because this is like saying e to what power equals a negative 3, which actually we saw up here. And if you take a positive base like e and raise it to any power, positive or negative, it's just going to turn it into some positive number. Maybe a fraction, but some positive number. So I'm never going to get a negative 3 as my output. So this won't lead to any solutions. So let's look at the other one. Here I just have to take the natural log of both sides again, but this is just the natural log of 2, and I can do that. So the natural log of e goes away, and I have x equals the natural log of 2, and if you type that into a calculator, you get about 0.7. Number 5 is a pretty basic exponential function. It's just 1,000 times this exponential term e to the 0.035t, and it equals 2,000. This looks like a pretty common interest problem where we have some starting amount, and then we're raising it to the 0.035t because it's building up interest over time, and then this would be like the ending amount. So this is kind of like figuring out how much time it takes for the initial amount 1,000 to double. So I'll just divide both sides by 1,000 to start out, and then I get 2 equals e to the 0.035t, and then I just have to take the natural log of both sides to get rid of that base e. So then this goes away, and then I have the natural log of 2 equals 0.035t, and then I just have to divide both sides by 0.035. Typing that into a calculator, you get 19.8. Number 6 is similar in the fact that we're starting with 500 and ending with 1,000, so it looks like this is an interest problem where the initial amount is doubling. But in these equations, it's usually being divided by n here, and then the exponent is n times t. So since you can see that the n value is 12, I'm actually going to think of this 60 as 12 times 5. And this really has nothing to do with solving this equation, it just helps you see what's going on. So this equation is talking about starting with $500 in an account, and then we're figuring out what the R value is. We're trying to figure out what the rate would be so that in 5 years, if the interest was applied monthly, we would end up doubling our initial amount of 500. So let's cancel these out and get 2 on the left side. Then we'll have this big set of parentheses 1 plus r over 12 to the 60th power. But in this problem, I'm actually not going to take the log of both sides because the variable I'm trying to solve for isn't in the exponent. I do have to get rid of the 60th power, so I'm going to take the 60th root of both sides, and you get 1.011619. In this case, I'm being as accurate as I can be, and I'm trying to be pretty accurate here because I know I'm going to have to subtract 1 from both sides next, so the only part of this number that really matters is the decimal place. And then the other thing is I'm dividing r by 12, so I want this to be as exact as I can get. So 0.011619 equals r over 12, and then of course just multiply both sides by 12. So after multiplying both sides by 12, I got that the R value is about 0.13943, and that would mean that the interest rate is about 13.94%. So in the last problem, when I said it was set up like an interest problem, it's because the equation looked so much like this. And these are the two different formulas we use for compound interest problems. So depending on how you invest your money, different accounts will have different ways of compounding their interest. Sometimes they will compound them yearly, monthly, quarterly, daily, or they might also compound them continuously. And of course, not just bank accounts have interest rates. Things like credit cards also have interest rates. It's just those are accruing interest that's working against you. One thing that's kind of interesting to notice about these two equations is that they're very, very similar looking. They both start with this p-value, which is the initial amount, and we use the letter p for principal. And both equations are set equal to a, which is just the final amount. And lastly, both equations have a t in the exponent. And of course, t usually stands for time. The only thing that's different about these is that one of them has 1 plus r over n to the n power, and the other one just has e to the r power. And when you're multiplying exponents like that, that comes from taking a power raised to another power. So you can think of this as 1 plus r over n to the n power raised to the t power, and do the same thing here, so e to the r to the t power. So in both of these equations, r stands for the interest rate, which has to be written as a decimal, even though we usually talk about an interest rate as a percent. But what's really interesting about this is taking a look at how you can get 1 plus r over n to the n power to become e to the r power. And if you think about the difference between these two formulas, one of them is for compounding interest after certain intervals, and the other one is for compounding interest continuously. If you take these intervals and just make them smaller and smaller and smaller, so yearly to monthly to quarterly to daily, and then if you took daily and brought it down to like hourly or by the minute or by the second, having smaller and smaller intervals would make it seem like we're starting to compound the interest continuously. And since n is the number of times that we're compounding the interest per unit of time, and what I mean by that is like if the unit of time we're measuring is a year, then if we're compounding interest yearly, then n would be 1. If we're compounding interest monthly, n would be 12 because it's 12 months in a year. Quarterly would be like 4 times a year, so n would be 4. And daily would be n equals 365. But the more often we compound interest every year, that's just saying that the n value is going to get extremely large. We could actually think of this from more of a calculus standpoint if you took the limit as n approaches infinity of this function. And you'd see that as n approaches these bigger and bigger numbers, that this function basically becomes the same thing as just e to the r power. And that's where a lot of the significance of the letter e comes from. Just the fact that this strange thing happens. The rest of these notes just include examples that would be better for us to take a look at together in class.